So hello everybody and welcome back. We're going to be continuing on, in fact we're going to be finishing up the 2011 Cimc paper. So this is the brand new paper, the 2011. It's for grade 9s and 10s for the most part, but of course younger students are very welcome. We're going to be looking at the last question in this contest. So that's part B, question number 3. Remember, in part B we need to have full justification, full final answers. This is the last one, so we should expect that this one will be the hardest. It will involve the most reasoning. But before we make too many other assumptions, why don't we just take a look at the question? So here we are. Question number 3 in part B. 6 swimmers swim lengths in a pool that is 100 meters long. They start at the same time from the south end of the pool, which we're calling S. And they swim to the north end, and they swim back, then back to N, and so on. So they just keep going back and forth, lengths of the pool. I assume these are idealized swimmers. Yep, they swim at a constant speed, and each turns around instantly at both ends of the pools. Okay, so it's basically just back and forth at the same speed, no slowing down, nothing like that. The swimmers are said to cross when they pass each other in the pool while swimming in opposite directions. So if one was just at N, so the north end, and one was just at south, and they're heading, so the first guy's heading back towards south, the second guy's heading back towards north. If they cross that way, then they're said to cross. If they were both at south and they both pass each other, then that doesn't count as crossing. They have to be able to high five as they pass each other. We also say that they cross if they arrive at N or at S at the same time. Okay, so we have a couple different definitions of what it means to cross. That'll probably mean that we might need to break things down into cases in this question. So they cross when they're going in opposite directions, but they're in the middle of the pool, or they cross if they both hit N or both hit S at the same time. Okay. So question number A, or question part A. Suppose that Alice and Betty cross at S after Alice has swum 400 meters and Betty has swum 600 meters. Okay? So they're both at S at this point, and that counts as a cross. How many times before this point did they cross? Okay. So let's think here. So Alice has swum 400 meters, Betty has swum 600 meters. How many times before this point did they cross? Well, it might be a good idea if we could figure out their speeds, because if we could figure out their speeds, we could start figuring out where they are at certain times. Now, we don't really have a whole lot to go on, but we know that it takes Alice the same time. It takes Alice to swim 400 meters for Alice is the same time that it takes Betty to swim. So while we can't figure out their speeds, we don't have enough information. If we had just one little bit of information about time, we probably could. We don't know their speeds, but we could probably figure out the ratios of their speeds, and that just might be enough. So this is what I mean. So even though we can't figure out the speeds, we could put in dummy variables for the speeds and at least get a ratio. So we'll call Betty's speed SA, speed of Alice. Or sorry, Alice's speed SA, stands for the speed of Alice. And Betty will swim at SB. Then we know the time it takes for Alice to swim 400 meters at a speed of SA is equal to the time it takes Betty to swim 600 meters at the speed of SB. So we can rearrange these, bring the SB over to one side, SA over to the other side, and in the end we're going to be able to see that SB is 3/2 the speed of SA. So Betty swims 1.5 times faster than Alice. That's something we can at least say at this point. How does this factor into when we start thinking about when they're crossing? Well, we have to ask ourselves, when might they be crossing? Could they cross during Alice's first length of the pool? How about her second length of the pool, so on her way back from north to south? See, Alice, we know, crosses the pool 4 times. So we could say, do they cross during her first lap, or her first length of the pool? Do they cross multiple times during her first length of the pool? And where do they cross? We can figure that sort of stuff out with their speeds. We won't know at what times they cross, but hopefully these ratios of speeds are enough to tell us where they will cross. And so we could figure out how many times they cross. So let's draw our little pool. So Alice, she goes back, then forth, then back, then forth. This is the south side of the pool, this is the north side of the pool. So she does 4 laps, while Betty goes back, forth, back, forth, back, and forth. And then they both meet again at S. They cross at S. Okay. So during Alice's first lap, so when she goes from S to N, we have to ask ourselves, how many times do A and B cross during the first lap? And then we can ask about the second lap, and then the third lap, and finally the fourth lap. So if they cross during Alice's first lap, since Betty's faster, Betty will have already reached N and will be heading back. Perhaps she's reached N a couple times and she's on her way back, but the point is, the pool will look like Alice going this far, some distance, we'll call it X, and Betty will have done something like this. So she'll have gone 100, 200, maybe 300, 400, some multiple of 200. Then she'll have gone a distance of 100 and she'll have come back. So Betty will have swum a distance of 200, some number of full laps, S to N and N back to S. Then plus 100 minus X. Okay. So what we need to do is, we have an equation in terms of X. Could we find out where X might be and what N might be? What possibilities for N and X there are, knowing that their speeds have this ratio. So knowing that their speeds have this ratio, so if Alice has traveled d meters, then B has traveled 100 meters. B has traveled 3 over 2 times that distance. So that's something we can set up. We have 200n plus 100 minus x, and we know that should be 1.5 times x. Okay, so that should at least help us a little bit. Okay. Distance Betty has traveled is 3/2 times the distance that Alice has traveled. Okay. Well, do we know anything else? We also know that this is Alice's first lap of the pool. So we know that x is less than or equal to 100. Then we can see that the right-hand side up here must be less than 150. And so it's pretty clear that no matter what we do, n is going to have to be 0. Notice that x being less than 100, this thing here is going to be positive. And 200n, well, that's going to be, if n isn't 0, that's going to be at least 200. So 200 plus some positive number, that's over 200. But at most, this can be 150. Okay, so n is equal to 0. So instead, we rearrange and we have 100 minus x is equal to 3x. Or really, 100 is equal to 5 over 2x. So x equals 200 over 5. X is equal to 40. Okay? So let's see if that makes sense. So if... That doesn't seem right for some reason. Oh, you know what it is? I screwed up. It's not 100 minus x. It should be 100 plus x, isn't it? Yeah. She does all these back and forths for 200, and then 100 to go to n. Yeah, we should probably write n in here. S. That way we know the size of the pool. It's plus x. 100 plus x. She's coming back this way, but it's still adding to her distance. I was thinking that this length here is 100 minus x. 100. No, it's not plus x. What on earth am I talking about? It's still 100 minus x. This distance here, 100 minus x. I had my original formula wrong. Now, the reason I was able to pick up on that is because we got our final answer of x equals 40. That would mean that if Alice has gone 40, that means Betty will have gone 60. She hasn't even crossed the pool once. They certainly haven't crossed. All right. So what have we got here? We need to rearrange this a little bit. Okay. So let's see if our reasoning is still correct. That Betty will have only done one lap, or Betty will have not done multiple double laps. So Alice's first lap, okay, x still less than 100. 3 over 2x is still less than or equal to 150. So if n was 1 or anything higher, we'd still have 200 plus 100, so that's at least 300 plus some positive number. That's definitely bigger than 150. So n is still equal to 0, so we're still fine. We just need to tidy up this equation at the end. So 100 plus 100 minus x, that's just 200 minus x. So we get a 200 over here. Okay, and then 200 times 2, that's 400. Divided by 5, that should, whoa, okay. That should be 80. So let's just stop and use the calculator there for a second. Yeah. So we're definitely looking at 80. And so that means that Alice has gone 80. That means Betty will have to have gone 120. She's gone 80. She's gone 100. And she has to come back and meet this little bit, 20. So it all works out. And that's just Alice's first lap. How about Alice's second lap? Why do I keep starting to write lop? Oh well. Alright, so what does Alice's second lap look like? She's gone here, and now she's come back a certain distance. So she's traveled 100 plus x. Is it possible that Betty has done, this, this, and then managed to come back 100 minus x? Okay, so what would that be? That would be 200n plus 100 minus x is the distance Betty would have gone. And so the same rules still apply. If Alice has gone 100 plus x, then Betty will have gone 3/2 times that. $100 minus x, just making sure that the formula's worked out, because it's rather embarrassing when it didn't work out the first time. But it should be. Going back and forth, all the way back to s, that should be a multiple of 200, and then she's gone just to meet her at 100 minus x. Alright. So, being her second lap, x is still between 0 and 100. So, we'd have 150 so this distance lies between 150 and 300. Okay, so it's looking like we might get an n equals 0 out of there, but we'll probably get an n equals 1. Certainly, we can't have n equals 2. Okay, so that's impossible because we know she has swum less than 300 meters. Okay. If n equals 0, well then she swum 100 minus x So our only chance is n equals 1. If she's done 2 full going back and forths of the pool, Betty has swum over 400 meters, which we know is impossible. If she's done n equals 0, then she has swum less than 100 meters, also impossible. So n's got to be 1. She's got to have gone s to n back to point S once. So then we have 150 plus 3/2 x is equal to 200 plus 100 minus x. So we can rearrange that. That's 300, 150. So we should just get 150 on this side equals 5 over 2x. So x should be 60. So Alice will have swum 160, and Betty will have swum 240. Wait, 240? Yes, 240. So does that make sense? Well, 160 times 3/2, that's going to be 3 times 80, that's 240. That one also works. So once again, we have another crossing, and that's during Alice's second lap. Third lap. And as I do this, I'm noticing that it's taking up a lot of our time to analyze each lap. So I'm starting to think, could there possibly be a general rule of thumb, a general formula to tell me where two people will overlap, given maybe the ratios of their speeds or something like that? It's something to consider, and hopefully we'll have enough information at the end of this third lap, or maybe at the end of this the fourth lap, which would complete this part, that maybe we can make a guess. Okay? So third lap, what does that look like? Alice has gone back, forth, so she's gone from S to N. And now she's come back just a little bit. So she has done 200 plus X. She has swum 200 plus X as her distance so far. Okay, now what about Betty? Well, Betty has again done something back and forth, back and forth, back and forth. She's done 200, multiple of 200, then she's come to N, which is 100. Now she's coming back 100 minus X. So Betty has swum 200 N plus 100 plus 100 minus X, which we will simplify to 200 plus 200 minus X. I'm noticing the numbers 100 and 200 come up a lot. It's something worth considering. In fact, other than this X value, we're just getting multiples of 200 in our expressions. I wonder if it was the same in the second lap. We'll make a note to look for that when we work out the fourth lap. But I'm thinking multiples of 200 are very important here. It is twice the length of the pool. All right. So the third lap, well, we need to equate these again. All right. Any distance Alice has gone, Betty has gone 3 over 2 times that distance. So what is that? That's 300 plus X equals 200N plus 200 minus X. Now, being the third lap, we can know that N is not going to be 0 because Betty will have already done N equals 1. She will have already gone from S to N back to S, just based on how the question, based just on the existence of the fact that she already swum one S to N to S, so one full trip. She's already done one full trip, and that was just in Alice's second lap. So we already know that N is definitely going to be at least 1. But let's take another look. So we know that 300 is going to be less than 300 plus X. it's going to be less than 400. Remember, x has to lie somewhere between 0 and 100. It could be equal. That's perfectly fine. That can happen. But it's got to be between 0 and 100. Okay, so what does that mean? Well, that means that 200n plus 200 minus x has to be between 300 and 400. And we know that x is less than or equal to 0. That means, what do we got here? Right, there's no way n could be 2, otherwise Betty will have gone too far. She'll have gone 400 meters, and our inequalities here say she has gone at most 400. So n can't be 2. In fact, n can't be greater than or equal to 2, we should say. Rule out all those numbers. So n's got to be 1 again. So she still hasn't gone that much further. She hasn't done 2 full trips. Okay. So then 300 plus x is equal to 200, because n is equal to 1, plus 200 minus x. So that's 400 there, 300. So 2x is equal to 400. I suspect I've done something wrong because now x is going to have to be equal to 200. What am I missing? Oh, no, sorry. 400 minus 300. Yes, of course, silly me. So x will be equal to 50. Okay, that was terrifying there for a second. I thought I'd screwed up for a second time in this question. So A has swum 250. I don't know what it is today, but I just can't spell. Uh, 250, that should be 350. So 250 divided by 2 multiplied by 3 is 375. Something has gone wrong here. Let me try and see if I can find out where that is. Oh, there it is. This should be a 3/2. I don't know what it is today. Maybe I'm just not feeling it, but I'm screwing up a lot of the little basic algebra. So this should be a 3/2 x. And these guys should be our familiar 5/2 x. So 5/2 x, we should get x equals 40. So Alice has swum 240 and Betty will have swum 360, and that makes a lot more sense. 240 times 1.5 is 360. So we're doing a lot better there. Okay. So now, time to look at the last lap. Well, what could that look like? So Alice has gone S, N, back to S, and now she's completed her third lap. She was at N again, and now she's gone a little bit of X. So she's gone 300 plus X. She's on her third lap. Or sorry, her fourth lap, her final lap. What's Betty look like? Well, we don't quite know. I mean, it's got to be between her, what was that, fourth and, between her third and her sixth lap. Gone back and forth, and then in order to cross, she has to be coming from this direction. She has to be coming from south, the south end of the pool. So she comes back that little distance, 100 minus X. So again, we don't know how many laps she's done. I'm going to guess she's probably done N equals 2 this time, just because I'm noticing the numbers aren't varying that wildly. So, oops, that's 200N, not 200 plus N. 200N plus 100 minus X. Okay. And I'm noticing, just because I was talking about it earlier, multiples of 200, I've got multiples of 200 here. 300 plus 100, that's 400. That's a multiple of 200. And X minus X, those cancel out. So I should just be left with 200N plus 400, which is some multiple of 200. I mean, yes, it's also a multiple of 100. That's the length of the pool, and that might come into it. But I'm noticing specifically there are a lot of 200 lying about. Things seem to keep coming up with 200. So you got to be aware of those little things, because this is taking a long time. This is only part A. There's got to be a faster way to do some of this stuff. Alright, so 3 halves of 300 plus X equal to 200N plus 100 minus X. Okay? So that's 450 plus 3 halves X is equal to 200N plus 100 minus X. So, what do we know here? We know 300 plus X. This fellow is going to be less than or equal to, so 400 less than or equal to 450 plus 3 over 2x less than or equal to 600. And so we can work it out from there that n will have to be, it'll have to be 2. Can't be 1, that'd be too low. Can't be 3, that'd be too high. So 450 plus 3 halves x equal to 400 plus 100 minus x. So we get 5 over 2x. That's a good sign. And then that's 500 minus 450. That's going to be a value of 50. So x will be equal to 20. Does that make sense? So how far has B gone? B will have gone 500 minus 20, so 480. And if we check it out with our calculator, that one still also checks out. 320 divided by 2 multiplied by 3, we're still going to get 480. So we're looking good. And since n had to be one specific value, we couldn't have crossed multiple times during Alice's fourth and final lap. So the next time they meet is at S. So in an effort to try and come up with a better theory of when they're going to cross, how about we list out when they did cross? So Actually, it should be where did they cross. So they both started at 0, 0, but that doesn't count. So if they've both gone 0 distance, they both met at S. So that is a cross, but it's not a cross. So that one doesn't count. And then where did they first cross? Alice had gone 80, and Betty had gone 120. And as I'm writing these numbers down, I'm looking for multiples of 200 is my goal, but maybe multiples of 100 are coming into it. Then when next did they meet? What was it? I think Betty had gone 240, Alice had gone 160, and then it was 240, and Betty had gone 360, and then Alice had gone, that was this most recent one, 320, and Betty had gone 480. Okay, and then they finally met up at 600. So these are the times they crossed beforehand. So we can answer part A. But let's take a look at the larger picture. Things I'm noticing from this table. The distance that Alice has swum between each of their crossings is constant. She goes 80 before their first crossing, then she goes 80 again to their next crossing, then 80, then 80, then 80. Same with Betty. She's gone a constant distance between each crossing, 100 to 100, 0 to 120, to 240, to 360, to 480, to 600. So that's one immediate thing we can notice once we have all their crossings listed together. So we can keep that in our mind. And another thing, just because I picked up earlier that there were lots of 200s and 100s, I noticed that the sum of how far Alice has gone and Betty has gone to before at a specific crossing adds up to 200. So 0, 0 where they started, that adds up to 0. 80 plus 120, that adds up to 200. 160, 240, that adds up to 400. 240, 360, that adds up to 600. Then these two add up to 800. Then these add up to 1,000. So not only are they adding up to multiples of 200, we hit every multiple of 200. 0 times 200, 1 times 200, 2 times 200, 3, 4, 5. I would bet that the next time they meet, they will have both swum a total distance of 6 times 200, which is 1,200. And I would bet further that they meet when Alice has gone 480 and Betty has gone 120. So, let's take a look at what the rest of the question is asking. We'll read both B and C and see whether or not we should develop this theory of when they cross better. So we've definitely answered part A. How many times before this point did they cross? They crossed 4 points. So we'll read the next two questions and see whether or not it heavily involves crossing enough for us to want to know when people cross, based on the ratios of their speeds and at what instances and how many times they'll be crossing. So, B. Suppose that Charlie and David first cross when Charlie has swum 90 meters. How many times will they cross again before arriving at S together for the first time? So I'm betting that if crossings do add up to 200, and this is their first crossing, then if Charlie has swum 90, David has probably swum 200 minus 90, which would be 110. So if we knew that for a fact, if we could prove that, that would make B a lot easier. How about C? Suppose that Farouk swims faster than Evan. Okay, well, Betty swam faster than Alice. That makes sense. Show that the length of time between two consecutive instances when Evan and Farouk cross is constant. So show that the length of time is constant. So that would mean something like, if we could show that, so Farouk swam at SF and Evan swam at SE, if we could show that the length of time was always 200 divided by SE plus SF, we'd be all set. So, I think it would make a lot of sense for us to try and develop a theory about when they cross involving the number 200. Alright. So let's jump back in. So if two swimmers, X and Y, they cross for the nth time, that's my guess, that if we have two swimmers, X and Y, I'm just going to assume that they go at different speeds, and it's their nth time crossing, whether it be at an N or an S or somewhere in the middle, then their total distance swum. So the distance X has swum and the distance Y has swum, I'm going to guess that is exactly 200 times N. Nth crossing, 200N. If they've gone 200N, I'm going to assume that they've crossed N times, or that's their nth time crossing, and if it's their nth time, then it'll be 200N. Okay? So that's my guess. I need to prove that in some way. And if I can't prove it, then we might try again at developing a bit of a theory. Maybe I was too hasty. Maybe there's something about Alice and Betty and their numbers. And if I can't do it, then I will probably just break down and do the whole question wrote by hand. Just write the whole thing out, written by hand. So, how would I go about proving that on their nth time crossing, their total distance swum is 200N? Well, we might want to try assigning some speeds to these guys, SX and SY. That is certainly something we could do. If they've swum 200N, so we're really asking two things. If it's their nth time, show it's 200N. If it's 200N, show that that's their nth time crossing. So, what could we do to prove this? I think the N is what's tripping me up. So I think it might be easier, because to say it's the nth time might suggest an induction argument, and that might work, but it's just not coming to me. So it might be easier to prove two smaller statements that if they cross, their swimming adds up to a multiple of 200. And if their swimming adds up to a multiple of 200, then they must be crossing. I'm hoping these are simpler statements because they won't rely on trying to figure out, oh, you've gone, if the total is 200N, then you must have gone 200M plus K, and then it's adding more variables that I just don't want to deal with. Alright, so two statements. If x and y cross, then the total distance swum is a multiple of 200. And conversely, if the total distance swum is a multiple of 200, then they must be crossing. Two simpler statements that doesn't rely on what exactly that multiple of 200 will be. Try and see for yourself how this implies the previous statement, that if it's their nth crossing, they must have swum 200 n. But we're not going to get into that unless we really need it. So let's try and prove these. Let's prove one of them. If x and y cross, then the total distance swum is a multiple of 200. So first statement, if x and y cross, then the total distance swum is a multiple of 200. So what does it mean to cross? Well, they can cross at S, so that means they both hit S at the same time. They can cross at N, which means they both hit N at the same time. And they can cross somewhere in the middle as long as they go in an opposite direction, as long as they can sort of high five as they pass. So there's three cases here. We know they're crossing, we just want to show the total distance swum is a multiple of 200. So if they cross at X, well, S looks like he's gone back and forth and back and forth and back and forth from S to N. S has swum a total distance we'll call it 200 times x. Okay? It's some multiple of 200. To go from S to N back to S is 200. So to be arriving at S, you must have done that multiple times. How about Y? What does Y look like? He goes back and forth and back and forth and back and forth. S and so we can say he swum 200y. We don't know what x and y are, but we do know that they are going to be sort of natural numbers. So in total, they've swum 200x plus 200y, a multiple of 200. Okay. If they cross at N, well, X will have gone back and forth and back and forth, and then he will go all the way to 100. So he'll have done some lengths from S to N, and then he'll have gone an extra distance of 100. Y is the same story. We just don't know how many back and forths he's done. So N is over here, S is over here. Alright, those were the easy ones. Those were multiples of 200, but they're the easy ones. Now we have to figure out what it looks like when they cross just at any old point. So now if they cross somewhere in the middle, so if they're crossing the middle, someone's coming from N, someone's coming from S. We haven't made any assumptions about who's a faster swimmer or how many times they've crossed beforehand. So we know someone's coming from N. We can just say it's X. X is just a label. It doesn't matter if it's X or Y. We just need a name of someone to work with. This just saves us from having to write out what is essentially the same argument a second time with X coming from S and Y coming from N. We can just switch the labels of these two swimmers and we'll get the exact same proof. So X has gone back and forth and back and forth, back and forth, and he's come to N, and now he's coming back a certain bit. So he has swum 200X. He's gone back and forth, back and forth, back and forth, X times. He's done X full trips, plus 100 to get to N, plus a distance of X. Y has swum back and forth and back and forth and back and forth and back and forth. And now he's coming from S, so this is his last stop, and then he comes all the way, and they meet. So he must come 100 minus X. That's how much distance from S he has come. So he has gone 200Y, and then he's done this little extra bit. Oh, that shouldn't be an X. We already have X somewhere. Let's just call it a D, I guess. D for distance. Or we could call it Z, or really anything we want. $200X plus 100 plus D. Well, this plus D and this minus D, they're going to cancel each other out. And just like with the last one, we're going to be left with 200X plus Y plus 1. So if they cross, total distance is some multiple of 200. So we can just say 200N. Now the bigger question, if they have swum a multiple of 200, are they crossing? All right. So the converse, it just means the reverse statement. So we've shown that if they cross, it's a multiple of 200. Now we show if they swum a total distance of a multiple of 200, they must be crossing. So suppose X has swum, we'll say he's done X many full trips and then plus some distance D. And Y has swum, not some, swum, 200Y minus D. So it hasn't quite got there yet. So in total, the distance swum adds up to a multiple of 200. Just any old multiple of 200. We can have X and Y and D be whatever we want. The point is, they have swum a total distance of 200. We need to show that they're crossing. So we have a couple cases. We have the case if D equals 0. D is between 0 and 100. D is 100. And the last case, D is between 100 and 200. Otherwise, we just absorb them. Right? If D was more than 200, we could just take 200 off of it, and incorporate that into x and into what our x and y are. So if d is 0, then both x and y have swum multiples of 200. They've done multiple full trips. So they both lie at S, and they're crossing. Okay? We could draw a diagram to illustrate this, but we've drawn a lot of diagrams, and by now we should be fairly confident in what we're doing. So if d is equal to 0, there we go. They both meet at S. How about d between 0 and 100? 100 is a special one. I think you can guess that's when they'll both happen to meet at N, which is a crossing. So if we have 0 less than d less than 100, x will have swum back and forth and back and forth and back and forth all the way to S, and then he'll have swum d. So he'll be on his way to N. He was at S, and now he's on his way to N. And why? Well, he's swum 200 minus d. But we could rearrange that and say that he's actually swum 200 y minus 1, so however much that is, plus 100, so he's gone all the way back to N, and then he's come back from N, 100 minus d. So he's come back to S, he's gone to N, and now he's come back 100 minus d. So it's clear that they're crossing. He's gone 200, y minus 1, then he's gone to 100 after that. So he's gone back and forth to S, then over to N, then to 100. 100 minus d happens to be distance d away from S, so they're going to cross, and they're going in opposite directions. So the case d equals 100 is just as easy as the case with d equals 0. Okay, and now the last case, which should finish up our theory of crossing and hopefully make parts B and C, we haven't forgotten about them, a lot easier. Okay, so if 100 less than D, remember we could assume that he's less than 200. I think I said less than or equal to 200, but that should probably be a less than sign. Him being equal to 200 is the same as being equal to 0. So x will have swum back and forth and back and forth and back and forth. And then he will have gone Actually, you know what? Before we draw this diagram, let's sort of make a variable substitution. We can rewrite D as 100 plus E. So we can more easily see that he is going 200x plus 100, and he's coming back from N, a distance E. Goes all the way to N, and then he comes back a distance E. It's heading in this direction. And Y is just 200, multiple 200, so he's at S. Then he comes back 100 minus E. Alright, so now both statements have been proven. Okay, it took a lot out of us, probably took a very, very long time. If you weren't sitting there explaining it to other people, it would probably go a little quicker. You could, I mean, these things are only worth 10 marks, so you could probably shirk a little bit of the description. You could probably turn this last case of 100D 200 into some sort of argument that says it's basically the same as the D is between 0 and 100, something like that. But the point is, we now have both statements proven. Even if you just sort of knew they were true or knew that first one was true, you'd probably only lose a couple marks. They are definitely true statements. So now we're in position to talk about, and we know every time that people are crossing, we know all of that. So let's take a look at the questions again. Suppose that Charlie and David first cross when Charlie has swum 90 meters. How many times will they cross again before arriving at S together for the first time? All right. So Charlie has swum 90 meters, and it's the first time they're crossing. Oops, not 100 meters. He's done 110. So knowing how far D has swum in a certain time it took C to swim a given length, we can figure out the ratio of their speeds. All right, and that immediately popped out from our theory of crossing. We might not have known when they first met. We might have had to do another 200 n plus whatever argument to show that they really do have to meet at 110. So our theory of crossing has already given us just a little bit of a benefit. So if we want to know sort of how many times they cross before they first meet again at S, we need to know well, anytime they're at S, C will have swum 200 C meters, D will have swum 200 D meters. Okay? And we know that 11 over 9, because that's how much faster D swims than C, then we get 11 over 9 times 200C should be 200D. 11/9 of the distance that C swum, D must have swum. So that gives us, what is that? 220C equals 1800 D. Okay. Can we reduce these anymore? Right? That's not necessarily the first time they've gotten together. So what are the smallest numbers C and D can be that make this true? Okay. So the smallest that C and D can be is C can be 9 and D can be 11. So how far have C and D swum? So C is 9 times, so he's going to have swum 1,800 meters. And he'll have D will have swum 2,200 meters. So that's the first time they meet at S. We want, after this first meeting, how many other meetings? Well, we know exactly when people meet. Given a certain total distance, we can tell how many times they've met up till that point. So they have swum a total distance of 4,000 meters. (4,000) over 200 for every single time that they cross. So we don't want the crossing at S, the one that they're doing right now, after 4,000 total meters of swum. And we wanted the crossing after their first meeting. We have 18 crossings. Okay? And we could probably actually figure out exactly when all of them are. But I think the question just asked, how many times will they cross again? So again meaning after this first time. So we don't include the first time, and before arriving at S together, so we don't include that last time when they meet S together. So 20 minus 2, 19. So their B part worked out much faster. We would have, 18 crossings, we would have had to work all those out before they even got to S. So our theory of crossing once again saves the day. Now last question, we'll read that again. Suppose that Farouk swims faster than Evan, so that the length of time between two consecutive instances when Evan and Farouk cross is constant. Okay. So I sort of hinted at a plan of attack for that one before. So suppose he swims at a speed e, so SE meters per second. And Farouk swims at SF. I think they said Farouk swims faster than Evan. We'll just clean up our notes here. Not that that particularly matters, but so between any two crossings, we know from our theory of crossing, we know it's going to be 200 meters. So the total distance swum between these two fellows, between any two crossings, 200 meters. So if combined they're swimming 200 meters, we don't care who does what work, but we just want them to be swimming 200 meters in total. So what we can do is we can just add their speeds together. So the time is 200 meters divided by SE plus SF. We just want these two fellows to cover the same distance, a certain total distance. And we know that this is constant because, well, 200 is definitely a constant, and SESF, we're told their speeds are constant. So there, in one page we were able to prove it. We knew that the total distance swum between consecutive crossings had to be fixed at 200 meters. We knew that. We worked that out. That was a consequence of our theory of crossing. And the time it takes for them to swim a total combined distance, well, that's just the distance we want them to swim divided by the sum of their speeds. They're not working against each other. They're sort of independent, just trying to make up a total distance. So that's SE plus SF. We know speeds are constant. That was given to us in the question. So not only have we shown it's constant, we know what constant it is in terms of their speeds. It didn't really matter that Farouk swam faster than Evan. They only include that so that the swimmers are not moving at the same speed, in which case they only cross every 100 meters. Okay. So that finishes off question number C, or part C. And yeah, that's it. It's a nice little paper, 2011 paper. It was very good. I liked the last question. We actually had to develop our own theory. We had to put it into practice. We hacked it together a little bit. Maybe if we hadn't caught that 200 meters, we would have been sort of stuck spinning our wheels as to what to do with part B and certainly part C. But, you know, we might have, if we read the whole question, which is a good thing, if you read A, B, and C, knowing what they were asking for ahead of time, while doing part A, you might have been looking for certain things, so a constant difference between their crossings. So that's something to consider. Reading the whole question is a very good thing. But, yeah, overall, I like that question. Very lengthy. Very lengthy. You sort of have to jump in and know what you're doing. Certainly, once you're done part A, you have to know, I need to find a better way to do this crossing stuff. And we did. Took us some time, but we definitely wrote out justification and a proof. We had our own little theory of crossing there. And by referencing that, B and C, they dropped out immediately. It was very quick to do B and C once we developed that. So a good question number 3 really made us think. I like it. It's a good first paper, 2011. So hopefully you'll join me as we continue on in this contest question video series for the CIMC. And yeah, so hope you all enjoyed it. If you did, you can throw a like on the video, whatever. But hopefully you'll join me for another contest in another video. So until then, I'll see you guys later, and thanks for watching as always.